working? Excellent. All right. In theory, we are live. Hey, everybody. How's it all going? What's your backgrounds? I love now everyone has interesting backgrounds. So, David, what's your background there?
I'm going to be rotating mine, I think.
Oh,
So
really?
what I decided to do, because I could mention my book a few times here,
Yeah, yeah, yeah.
and I got a background of the book, and this is just one of the pages in the book.
Oh, okay, okay. All right.
So what this one actually is the disc of Enheduanna,
Oh,
uh, and the book is about the moon, and everything in the book is about the moon going through human history.
Right.
And Enheduanna is the first person we know who signed her name after writing something. So she's the first author, and she was a lunar priestess in Mesopotamia. So the moon connects with the very first author in
Oh, cool.
history.
Okay.
Now that's
And
from that part of the book.
Carolyn, what's your background?
it's supposed to be some kind of an alien planet. It's
Okay.
painted by a fellow. It's from Digital Blasphemy, and I'm a lifetime member, so I could use any of his backgrounds on Zoom.
Oh, good. That's nice.
Yeah.
I have a Borg chip that I use sometimes when
Ooh.
I was like, let's see, where's my? That'll go right in the middle of that, though, won't it? Yeah. Okay. All right. So where's the one that? So when I was running
Oh yeah.
I was running a role playing game with a bunch of people, and so we were on the Borg ship, and so I was running that.
Well, I thought since I was talking about habitable planets tonight, I'd put up a habitable planet.
That's awesome. All right, I'm going to say hi to a bunch of people. You all had a chance to say hello to me in the chat. So hello to Andrew Planet, Ben Kalo, Beth Johnson, Bill Smith, Brian Thomas, Douglas Clausen, Ian Farquhar, Johnny J, Johnny Zed, Larry King, Michelle Joy Wexler, Nancy Graziano, Rich Wilson, Roger Haskins, and Ronald McCoy. Hey, everybody. And that's your chance. Say hello. Zapfan. Did I already see Larry King? Alex Disbland? Yeah. So, did have you guys been watching Mars? We went out last night and got a chance to look at Mars before I guess it disappears at opposition. That's what happens, right? We tried last night. It was good. We could see it was pretty low to the horizon, and so we could see the my telescope. I don't know if you could see my telescope's kind of low. It sort of shift its position. Anyway, so we were able to see like some dark regions on the surface of the planet. Couldn't see the poles though. So, which is usually
Was it the part of virtual star party?
No. This was just me taking my telescope out last night. So, hopefully for the virtual star party this weekend, we'll get a chance to see Mars. Assuming California isn't still putting out a lot of smoke, because we had to lose. We lost a lot of telescopes to smoke last week, so we had to cancel. Yeah, people are telling Mars. Brian Thomas is saying that Mars was as big as the moon. No, it wasn't. Don't you say that. I've just, man. Oh,
Oh, but the sun is turning the color of Mars here, so
is that
from all the smoke.
is that science? Yeah. Okay. Yeah.
Yeah.
All right. Okay. We're hit the 5-minute mark, so why don't we'll get started. So I'll put you all back in your boxes. There's me. Let me find my introduction, and here we go. Hello and welcome to the Weekly Space Hangout for Wednesday, October 7th, 2020. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about the first direct observation of exoplanets around Beta Pictoris C. Is Earth the best habitable planet? Is this the best we could do? Germany planning its first spaceport, and maybe more. Joining me this week, we've got, Carolyn Collins-Peterson. Carolyn, welcome back. You're muted. Oh, rookie mistake, Carolyn.
Sorry. Hi.
There we go. Last time you were here, we were talking about how smoky it is in Colorado, and it's still smoky in Colorado, isn't it?
Yeah, it is. We've got 3 fires going.
Oh,
all pouring out smoke.
Oh, when's that? And it's like the snow's starting to fall, isn't it?
We've already had one snowfall, but
Yeah,
it went
you'd think
away.
snow would put out fires, but apparently not. Oh well. From the other side of the world, we've got. I guess my two co-hosts don't know which one of them I'm going to say. We've got Alan Versfeld. Alan,
Hi, yes.
you're from the southern
Oh,
hemisphere of the world.
yeah, no smoke out here. Just clouds. Rainy season just started.
Yeah, it's your right. Of course, it's your.
Yeah.
Well, I guess you're out of your leaving your winter, right? You're starting to move towards summer now.
Yeah, trees are getting green, rain is falling, and there's no astronomy. It's it's just
Right.
miserable and
Yeah.
wet.
Well, that sounds like Western Canada all the time. So
It feels very English at the
yeah, it
moment.
does feel very English. Yeah, exactly. Yeah, no matter where we go, it just ends up feeling very English. And then of course we got Nika Klimic. Nika, welcome back.
Hi, hello. It's rainy season here as well in Germany.
Yeah, we have the same climate as well. I think us and where you are. Good. Well, I'm glad you're able to make it back. I know you were sick last couple of weeks ago, so you're back.
Yeah.
Awesome.
So I'm back.
All right. So before we get into our special guest this week, I just want to give a huge shout out and thank you, as always, to our good friends at the Weekly Space Hangout crew. They are the executive producers of this show. It's because of them that we have all the amazing guests, that the whole machine really just kind of runs. Like, if there was no Weekly Space Hangout crew, there would be no Weekly Space Hangout. That is what I'm saying. So if you want to be a member, if you want to take your love of space and astronomy to the next level, join the Weekly Space Hangout crew. Totally free. Go to wshcrew.space and they will give you your executive producer credentials so that you can then reach out to your favorite researchers, astronomers, astronauts, Nobel Prize winners, and have them show up here on the show. So go to wshcrew.space and they will hook you up. All right, joining us this week out in space, we've got David Warmflash. David,
Hey,
how's it going?
hey, Fraser. Hey, thanks for having me back. It's great to be back. I can't believe it's been, what, 2 years since I've been on the show?
Has it been 2 years? Yeah, and I know we've been talking a bit back and forth on the Twitters, but you, who are you? What do you do? For people who haven't seen you
Now,
before,
I'm a space doctor. That's the easiest way to put it. So,
space, but not the regular kind of space doctor. You know, the PhD
no,
astronomers
real
that we normally
doctor.
have. Yeah,
Space.
yeah.
Yeah, I'm just kidding. But I research astronaut health issues as well as other space life science issues, all the way into astrobiology. And it's the astrobiology part, which is why I have Venus behind me
Mm-hmm.
with some Apollo style hardware. That's another thing from the book of mine from last year, Moon in Illustrated History. The Apollo extension program, which was a way to have like more advanced Apollo missions that was planned until the budget was cut. There was actually a plan for a human flyby of Venus
Yeah.
in the early 1970s. It would have been really cool. And it was canceled in the Nixon administration. But I have it up here because of the phosphine discovery in the Venusian atmosphere. So it'll be an appropriate thing to put on.
So you've got a new book, but before we talk about the book, I want to talk about your. You've got is it a NIAC phase 1 study that you're working on?
It's is SBRI, NASA
Okay.
SBRI. So it's Small Business Research. I forgot what the I stood for.
Innovation research. Yeah.
Yes. Yeah.
And so you are researching mixed reality holographic training, which is so cool. So can you explain this project?
Yeah. So what the mixed means is it's a mixture of actual physical reality, the patient, and augmented reality. So there'll be kind of holographic projection. And we're working right now with a system called Microsoft HoloLens that you may know. And you wear a head device and you can see whatever the algorithm is projecting around your field, which could be over the patient, on the patient, and in front of you. And the purpose is to be able to guide somebody, such as a crew medical officer, through either a complex medical procedure that he or she is not trained or practiced in performing, or a surgical procedure.
Right.
And all you have to be able to do is cut along the dotted line, basically.
Anybody could do it. I mean,
Yeah.
when you think about the upcoming missions and the amount of autonomy that the astronauts are going to have, I mean, they are going to be, I mean, even the moon is right around the corner from Earth. But
Yeah.
if they're off to Mars or perhaps to Venus, they're going to be months away from any kind of help. And the kinds of things that can go wrong on the mission are just too numerous to even count and too numerous to train for. I mean, at a certain point, they just would be training for every possible disaster. So it sounds like somehow carrying along this kind of capability is a pretty great way to be able to extend the ability of people who have a certain level of training. Is that sort of NASA's thinking?
Yeah, and also it would be able to integrate with any surgical robots that are available. We don't know yet the full makeup of what the whole package will be in terms of exploration class missions and the medical package. Will there be surgical robots? What type of imaging capabilities will be there? It all hasn't been decided yet. It'll probably evolve very gradually. We know there won't be an MRI machine because it's just too big and heavy. We know certain things will have certain things, certain capabilities, and not others.
Well, I don't know. Maybe there's enough radiation just in space itself. Like just stand on the, just watch this cosmic rays are going through their astronaut buddies. So, I mean, we've got some kind of similar situations, like, for example, with Antarctica. Does that give you some kind of idea of the kinds of issues that may crop up over the course of a long mission? I mean, a mission to Mars, for example, that's 2 to 3 years, depending on which windows you go with. What can go wrong in that length of time?
Well, I mean, even anything can go wrong in a mission extended over a few weeks, as we know from the Apollo lunar experience, with Apollo 17 being the longest human mission outside the geomagnetosphere, outside Leo, was something going on 2 weeks, I think about 12 days, and things can go wrong. You can't get back to Earth immediately. So you have to do more than stabilize an astronaut who's in serious condition. You actually have to do some treatment. So we think we'll get our space legs for this on the lunar missions in the Artemis era, and then we'll be able to carry those over to Mars.
So you'll have, like, at some point the Artemis astronauts will perform some kind of basic surgery on each other, just to find out what happens in the lunar environment. Hal McKinney asks a really great question in the chat, which is how would augmented reality handle the latency, the time latency in some kind of medical procedure? How would you deal with that situation?
Well, we are in phase 1 right now, which means we just have a 6-month startup to do the proof of concept and look at a few different procedures. And we're moving through on a chest tube procedure, thoracostomy, which means you're making a hole through the thorax, through the chest or the side of the upper thorax to gain access to the intrapleural space. And we're also looking at surgical airway, which is, let's say somebody can't breathe and can't be intubated. So we have to go in through the throat. These are some very basic emergency needs, but there are particular needs for this in a space flight environment that we can imagine, because if we take even the new XCMU spacesuit that can operate at pressures up to 8.2 psi, we can still get a rapid decompression leading to a barotrauma injury, including pulmonary barotrauma, and then a condition called a pneumothorax is a pretty likely outcome, and it's a pretty simple, straightforward thing to treat on Earth.
Right.
But it needs decompression of the chest, and you can start with a needle in there, but then you got to get a tube in there. And so we're working with consultation from the Oregon Health Sciences surgical education department to look at what are the simplest procedures to handle something like this, that somebody like a medical student or somebody like me, who's an MD but not a surgeon, can handle.
Right.
And so just from the initial response from the guy who's working with us in that department, we already made a decision to go with a narrower kind of tube called it pigtail, which is coming into use a lot more frequently these days when you have a simple pneumothorax and not, say, full of pus
Right.
or full of blood.
And so I think, I mean, the interesting part is going to be, as I mentioned, like where for these longer missions where various crew members are going to have to be able to do multiple jobs, it could very well be that that the surgeon on the is the one who needs the procedure, and so someone's going to have to be the backup surgeon, or maybe there's some issue that has taken out both the main surgeon and the backup surgeon, and then the third surgeon, the third person. So it sounds like this gives you a pretty powerful backup solution to be able to almost bring anybody willing to cut human flesh to give them some level of ability to be able to solve a problem in a disaster.
Yeah, we're starting off with procedures for which basically you have to be able to hold a scalpel, cut through tissue without your hand shaking too much, and you have to be able to suture and do some of the basic suturing patterns and inject with needles and get things in and out like that. If you can do that, then the system will tell you, make your incision here. There'll be a projection. You follow the projection. And here, let's say, put in vertical mattress sutures this way and that. And it will say, go from here to here, stop here, go down to the next layer, and so forth. So you don't have to have actually done the procedure ever in your life.
That's, I mean, not just space itself, but I can just imagine there's so many situations, even just down here on Earth, when there have been disasters and issues, and people just haven't been able to. I mean, even just to be able to, I know with HoloLens they demonstrated people just being able to replace their light switch. Like it's just, there are things that we have to do that require that you don't even know where to start. And if you could just have some big arrow going, cut here, unscrew this. You can imagine even from an engineering standpoint as well, right? Now, the environment of space, how much do we know about how different the environment of space, especially, say, microgravity, what impact that would have on some of the procedures that you would need to do?
Well, if you're talking about weightlessness, say if you're like an ISS scenario, that would be pretty hard. I mean, there's been a lot of studies on KC-135 flights where you have, say, 90 seconds of weightlessness. So you really can't do that much. And people have tested surgical procedures. It's really hard. It's hard to handle fluids. So, but we're imagining this being used on the moon, where you have 0.16 G and then later the 0.38 G of Mars. If we go to Venus and we're floating in the atmosphere, we got like 0.85, something like that.
Yeah, regular gravity, pretty much.
Earth.
Yeah. Have you seen The Expanse?
Yeah.
Yeah.
So
So
the first season or two.
okay, well, in a season, there's a disaster on one of the ships, and a whole bunch of people are bleeding. And they said that in microgravity, bleeding is the kind of thing you can't stop it. I don't know if we have any. Is there any science behind that? Do you need gravity to be able to recover from some kind of injury?
If you put pressure on the bleed, so if it's on the limb, and you put just a standard tourniquet, that will stop it.
Right. Okay.
And
Okay.
if it's not so bad, it's just basic physics. If you have to, the pressure put on has to exceed the pressure, the hydrostatic pressure of the blood. So that's
and
what you need.
then the body will be able to coagulate. So if you haven't gotten to that scene, I would love for you to later on to hit me on Twitter. Just go, okay, I saw it, and totally legit, or you could say fully debunked. I would love to know what you think. Or they're talking about internal. That's right. Trey Harmon is saying it's internal hemorrhaging, that you would have problems inside if you have bruises and things like that. So I
But
don't know.
you would have a fluid shift. You have a cephalic fluid shift, a fluid shift up toward the head if you're in weightlessness,
Yeah.
and that will affect everything too, because that gives you a higher blood pressure above and a lower blood
Right.
pressure below, and it changes how you do just about
Yeah.
everything, including how you get vital signs. And
Yeah. A lot of people are sort of noting that this technology is sort of shifting towards, say, the Holodoctor from Star Trek, Voyager.
yeah,
You know, that idea of, please state the nature of the medical emergency,
yeah,
that you could get to this point where the computer can help you through a lot of the disasters. And I can imagine a version of that. I mean, I'm sure there's engineers and mechanics and stuff thinking of the exact same thing. What if you need to take apart a CO2 scrubber and your mechanic is incapable of doing it and your lives are on the line? Boy, would a HoloLens walking you through the process really make it. So
yeah,
it sounds
yeah,
amazing. It sounds like a great technology.
yeah. And
Um,
you brought up Antarctica.
mhm.
It's the psychological environment too. There actually was a case in the early 1960s on a Russian ship off the coast of Antarctica, and a doctor had to perform an auto appendectomy
On
on
himself.
himself,
Yeah.
and he did it with mirrors.
Yeah. But could he have just as easily marked off on his body where to cut and sort of showed one of his crewmates what to do and then let them do the work? I don't know.
I think he might have had an assistant
Yeah.
helping him
Yeah.
retract things. You can't just say cut here. There are layers. You got
Yeah.
to go through step by step.
But I guess that's the kind of thing that the HoloLens,
Yeah.
as you went through the layers, you would see
Yeah.
the next layer, and the HoloLens would be telling you what to do and what this layer is and how to
Yeah.
treat it properly and how to
You got to
suture
go
it back
through
up.
layers, and then you got to pull something out. You got to pull out the cecum and then
Right.
find the appendix on there.
And then you've got to suture back out through the layers on your way
Yes.
back out again.
Yeah.
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 So like you don't want to skip steps.
Yeah, and you got to put Kelly clamps pulling each layer of fascia and muscle apart, and those simply get laid on and pulled apart. So if you're in weightlessness, I don't even know how that would work.
Oh, yeah.
But in low gravity, it should be fine.
Yeah. We need to get to some kind of artificial gravity
Yeah.
as soon as possible.
Yeah.
Have you been watching that at all? Are have you been thinking about? I know this isn't exactly your field, but I'm always trying to find out if anybody's watching anyone working on any kind of artificial gravity for space, from a medical standpoint.
I actually did some research in artificial gravity
Yeah.
at the NASA's Ashton Graybill Laboratory, located at Brandeis University. I did a training in space biology and medicine there a million years ago with the crew there. And it's a big room. The whole room rotates, and we were measuring the effects of Coriolis forces
Right.
on the eye. So it even affects your eyeball directly. So
Yeah.
not just talking about eyes moving off in the wrong way from nystagmus resulting from Coriolis forces on the fluid in your inner ears, but actually direct Coriolis effects on the eye.
Wow.
And so if you're in a rotating environment, if it's a small environment, so it's a very short axis of rotation, you have to take that into account too. If you're doing a procedure requiring manual dexterity, it might throw off your hand. It might
Wow.
you're not expecting something.
Yeah, and so you got to make the choice. Do you want to be in some kind of gravity where you can't see straight, or do you want to be in weightlessness where you don't have the benefits of gravity? It's absolutely going to be a fascinating challenge. I reported on this a couple of years ago. There are these centrifuges that are fairly small. Like people, they're trying to work out what is the smallest possible centrifuge that a human being can endure. So not, what feels like you're walking around in normal gravity, but what is the smallest one that will give you that benefit of a G-force, but that you aren't just going to be vomiting all over yourself nonstop. And it's actually pretty small, and you can become accustomed to it over a fairly rapid period of time. Like you could fit one of these inside a Falcon 9 fairing and attach it to the International Space Station. But
Yeah, there's been work on that.
yeah.
Larry Young, who was at, I don't know if he's still there, if he's retired, but at MIT, had a very small, like basically on human size centrifuge
Yeah,
where it's basically the length of your body is the axis of rotation.
yeah. And so
Has
and
a
it's
mitigation.
not comfortable, but it is endurable, and in theory you'll get the benefits of the spinning, which is, the as microgravity is
Yeah,
constantly, has all those other negative health issues. All right,
yeah,
let's get to your book. You wrote a book
sure. Yeah.
again.
Yeah, here, I'll put that background on here. It's called Moon in Illustrated History.
And every time
Uh,
you hold up your book, it disappears into the background. So just to warn you,
yeah, so I'll just make it the background.
or just hold it up right in front of your face. Oh,
Well, there it is. Okay. And I also can.
awesome. So what's the book about?
Now, the book is, it goes through history, starting with really the Earth, because the moon is involved in very early in terms of the origin of the moon took place very soon after the origin of the Earth. A lot of conflicting hypotheses about how that happened exactly. The giant impact hypothesis has been losing ground, and the multiple small impact hypothesis has been kind of easing in on that, maybe catching up a little. But it's the same idea. You have debris orbiting Earth and it coalesced into the moon.
Right.
Everybody agrees that happened. But we go from there, 4.5 billion years ago, altered time, the origin of life. Moon might have had some impact on that, especially because of the tides, because the moon was a lot closer. So the tides were huge, and you'd get more mixing between liquid and solid. And going up all through human history, a lot of the book is on ancient history, a lot of things happening with the ancient Babylonians and the ancient Greeks. In fact, I hear is Anaxagoras got in trouble for saying the moon was not a god and the sun was not a god, and it was all part of a whole political thing with uh, the enemies of his Pericles, not Pericles. Yeah,
Right.
the great politician. Yeah, he
Right.
got into trouble. He was really um, overextended himself, which ultimately led to the Peloponnesian War. But they couldn't go after him, so they went after his friends who were weaker, including Anaxagoras, the first philosopher to bring philosophy to Athens.
Right.
And so there was a law in the books about, you're not allowed to, it was blasphemy to say that the moon and the sun are not gods, even though this is classical Athens. You think you're safe there, but they weren't. And he ended up being exiled to some small little island. And I go through the Middle Ages. There are some of the Arabic researchers who use the moon. What else we got here? This is that's somebody using a device invented by the Jewish philosopher Gersonides, called Ralbag in the Jewish Talmud, which he was an astronomer and a philosopher, and he's thought to have, by looking at the changing brightness of the moon as it went through its orbit, he was able to extrapolate to changing brightness of planets like Mars. And from that, he was able to extrapolate a very approximate distance to the stars of the Big Dipper. He got the order of magnitude more or less right. He said the equivalent of what we would call 10 to 100 light years, which for this was the 14th century.
Yeah, not
so
bad.
for those days, it was a pretty good guess.
Yeah.
This is long before Frederick Bissell in the 19th century actually was able to do a parallax
Well,
measurement.
it sounds absolutely fascinating. We're pretty much out of time, so but I know that you've got a couple of copies that you're going to be giving away, so people can follow you on Twitter to.
I'll
learn
give you
about
one
that?
copy for this show. So I have two more left, one for
All right.
this and one for another show. And so the way we both get the best out of it is if you can do this if you want, but if you know, and I'll do, you can say, I can tweet the promotional material for this episode,
Yeah, follow
and then
you on
whoever
Twitter. We'll put a link
retweets
to you. What's your Twitter handle?
Cosmic Evolution.
Cosmic Evolution. All right, so we'll put a link in the show notes if people want to follow Cosmic Evolution on Twitter. You'll have some instructions about how you're going to be giving away a book, and people can follow there. That sounds great.
You retweet my tweet about this episode.
Oh, yeah,
and then I'll take the people who did that, and I'll pick one out of the hat.
Like I said, I'm not going to endorse that kind of. Like I said, we have very specific laws in Canada about how giveaways work. So
just one stipulation is that the publisher can only mail it as far as the UK.
Right.
So if you're in Canada, the US, that's fine.
Yeah.
The UK, that's fine, but not. Sorry if you're in Australia. I asked them, they said no.
Yeah. Understood. All right. Well, you're going to stick around for the rest of this episode. So if you have some other, we have some other topics to cover, and if you want to jump in, feel free. If you have some questions, jump in. But again, thank you so much for joining us on the show and for explaining the fascinating research that you're working on. And good luck with getting your grant and seeing how this all works out. I think this is going to be key for the future of space exploration. So good luck with that.
Yeah, thanks, and thanks for having me on the show.
On. All right, let's move on to the some of the news. Alan, this is the big story, I think, one of the biggest stories of the year, so I definitely want to talk to you about this first.
Yeah, so it's this is an interesting one. It's the first time that a planet that had previously been discovered using the radial velocity method has been directly visually confirmed. It's Beta Pictoris C, which would be the second planet that was discovered around Beta Pictoris. I say visual, it's actually near infrared, but in for intents and purposes, it's directly it's
a picture of an exoplanet. I'm gonna put the browser shot up so people can see the story, and you guys can see it as well. So you can see what we're sharing here. Look at this. So can you explain to people sort of what they're seeing in this picture?
Yeah, so in there we are looking at, that is Beta Pictoris. We are looking at, it has several dust or debris belts and two planets, B and C. B was actually discovered first, and that was discovered directly visually, but we don't know very much about it. It was originally imaged in 2003, actually. And it was only a few years later in 2008 when new data reduction techniques basically brought the information out. It still wasn't the first ever directly imaged planet. That was several years before. But the discovery today now, this is the first time a planet around Beta Pictoris, well, first time any planet that has been, it's the first ever confirmation of a radial velocity detection visually. And so what we now have is quite a lot of information about this planet directly. We know its orbital period. We already knew that. We now know its brightness. And so we have spectroscopy on that image using the same instrument. It's the gravity instrument, which I'm embarrassed to say I've not been able to figure out what that stands for. It's an instrument at the VLT. Everywhere on the ESO websites and in all the press releases, they just say gravity.
But no one will say what it means, what it stands for.
It's possible that they broke with tradition and never bothered coming up with a backronym for it. Or an initialism or whatever the term.
But they capitalized it.
I know.
That's not right.
That was a bit frustrating. I could not figure that out.
So let's talk about these different techniques. So I mean, the planet itself was first found using the radial velocity method, right?
Yeah.
And so go ahead.
Yeah. So radial velocity detections are basically where you look at the spectrum of a star, and you're able to measure its velocity towards or away from the Earth. And if you measure it precisely enough, you can see how that velocity varies very slightly.
Yep.
And that comes from the planet swinging around the planet slowly. It wobbles slightly just from, if you swing a bucket around, you yourself will shift your balance slightly. It's the same effect.
That's a great analogy, actually. I like that one. I've never used that one before, that you're spinning a bucket filled with water around and you're going back and forth as the bucket is spinning around.
We
I
always
think
use
that's
it just to try and, to explain orbits very inaccurately with centrifugal force, but it works here.
Yeah.
So we already knew about that, but Beta Pictoris it's a very bright, hot, young blue star. So direct visualizing is quite difficult. It tends to wash out the light, and this planet C is quite close. It's close enough that it's very, very difficult to make out separate the lights from the planets.
Yeah. But when we look at the picture, we don't see the star. Right? In the picture, you've got this nice dark, you've got the dust disk around, you've got planets B and C, but there's no star in the middle of the picture.
Which picture are we looking at here?
Well, the one,
the one on the left.
The one on the left, yeah. So this is me setting you up to talk about a coronagraph, but
Oh, of course, yeah. That's you have to do that. Even in our own solar system, if you want to observe comets nearby, the only way to deal with that glare is to block out the sun, put something physically in the way. Although I can't confirm that's specifically what they've done here. I know that the angular resolution of the VLT with this instrument is very, very low. Yeah. And it's I believe this is, well, no, I'm not going to go speculating with it.
But I think I mean, what is just amazing is that you're seeing, you've got pretty much the biggest telescope in the world, right? You've got the Very Large Telescope in Chile, and you've got the combined light of all four telescopes working together using their adaptive optics and their interferometry to act like one big telescope. And we are seeing the surface of Jupiter-like worlds orbiting another star. And we're not just like measuring the wobble of the star. We're seeing the picture of the planets, which is it's just so mind-bending that this is where we are now. That 25 years ago, we only just barely knew that there were planets, and now we're seeing pictures of them.
And unusually, we know more than I think with most exoplanets because we don't just know its distance and its orbital period. We now know its brightness directly, and so we can infer, take educated guesses based on its mass. We know its mass about what its density and composition must be. This one's very bright. It's several Jupiter masses. It's got an orbital period of about 1,000 days, which in our solar system would place it somewhere in the asteroid belt, I think. We don't have this information yet on the first one that was discovered visually around there, interestingly, because it's got a much longer orbital period. So there just hasn't been time.
Right.
We need to keep observing it's a 28-year orbit. We're going to have to watch it for a while to measure its mass. But it's all these firsts. You start to lose track of just how many amazing discoveries we're making.
Yeah. One of the things that I really like about this, a lot of the new instruments that are being put onto the Very Large Telescope are technologies that are being tested out for what's going to be functioning on the next generation that comes after the Very Large Telescope, and that's the Extremely Large Telescope. That's where someone has to point to the XKCD cartoon about the different telescope names, but that you're taking these technologies that are working on 4 8.4 meter telescopes, and then you're now going to apply that to a 39 meter telescope that with its coronagraph, with its ability to direct image, is going to be able to do things like observe the atmospheres of Earth-sized worlds orbiting sun-like stars or out there in space. Amazing. So we are, here we are in 2020. The Extremely Large Telescope comes online in 2026. We are 6 years away from this, just seeing this picture of planets orbiting another star, of being just the beginning of what comes next. So
any bets on the discovery of phosphine on an exoplanet?
Yeah. We talked about this. I did this in a question show, just about how like, we're so lucky that phosphine was found in Venus, because we can double check it. We can send a spacecraft to Venus and go, what's causing, is it volcanism or is it actually life? And if it's life, then that makes the discovery of phosphine on other planets very exciting. But if it turns out it's volcanism, then it's not so exciting. Suddenly it's a natural process that can account for it. So we're really lucky to start finding some of these if we can find more of these biosignatures on Venus.
Mm-hmm.
Yeah, absolutely terrific. You're going to say something before I shift over?
I was taking a breath.
Oh, okay. All right. Yeah. I believe David can agree that that's important. All right. Carolyn, what have you got for us?
Well, I have what sounded to me when I first saw the story is something like my planet's bigger than yours. It's better than yours. But it was basically a story about exoplanets that are super habitable, and meaning that they're more habitable than Earth. And what that really means is that they have better conditions for life than our planet does. And then maybe their stars have some characteristics that contribute to their being much more welcoming to the formation of life ultimately. Now, on the back of that, there's a story that just came out today about super flares basically cleansing the surfaces of planets. So sending out large, clouds of UV. So, but that's not these. That's not the ones we're talking about. But that story did come out today. So, so there was three. Yeah, go ahead.
Oh, okay. So I was just going to say, so like, what makes a planet super habitable?
Well, that's what these three guys wanted to know. So you're going to have Dirk on next week. Dirk Schultz and Makuk, and Renee Heller of Max Planck and Ed Guinan of Villanova started sorting through this subset of known exoplanets to see if they could figure out what the criteria are for super habitability. So for habitability, we know that it has to have, for life as we know it, it has to orbit in the Goldilocks zone, which is the orbital zone where liquid water can flow on the surface. You need water for life, so that's important. But beyond that, what are their characteristics? And so they started looking at these things, and there's five of them. There's the three we know about, the two we know about. The age of the star is really important, and it has to be shining long enough to permit life to arise. So the sun, for example, is 4.5 billion years old. It'll live to be about 10. And it took about 4 billion years for life to get started here. So a shorter lived star wouldn't live long enough to really foster the development of life. Once life gets started, it blows up everywhere, but it just takes a while to get it going. So these scientists have suggested that the sweet spot for life formation is actually about 5 to 8 billion years. So that makes the Earth kind of precocious by comparison. So
I think I missed something there. You say it took 4 billion years till life gets started here, but life got started a lot earlier than that on Earth.
Multicellular life.
Well, about 3.8 billion years ago.
Multicellular, about
well, we're
500
talking
million
about
years
complex
to 2
life,
billion years ago.
So complex life. Yeah.
But simple celled life, celled life.
The moment
a few 100 million years.
Yeah, the moment Earth was was not on fire anymore, then you got
but they're talking about complex life. I should have probably clarified that. So to do this, you can have these single cell life forms going for quite a long time, but you want to cook up the more complex stuff. You have to have the conditions for that. They're saying, let's look at longer lived G-type stars. Like the sun, but living a little bit longer, or maybe even some of the cooler, longer lived K-type stars. The point is you need plenty of life for plenty of time for this more complex life to really take a hold on a planet. For the planet itself, for superhabitability, it has to be, they're saying for superhabitability, it needs to be about 10% larger than Earth. That would give it more space for land masses to provide more homes for life. More mass would also give it a stronger gravitational pull, a chance for holding onto a stronger, more nurturing atmosphere. Atmosphere should be wetter and warmer. And, we can see that here on our own planet. Places with a lot of warmth and water, like the rainforests, have a lot more, varieties of life. So all these factors, an older, longer lived star, a planet with higher mass, bigger than Earth, more land masses orbiting in the Goldilocks zone, that's what would make it a super habitable planet and better than Earth for the fostering of life. So then they kind of end the whole thing with, well, are there any of those out there? And they've only looked at 24. And so far, they haven't found any that have all of the factors.
Oh, okay.
They found one. Yeah, they found one, And this is all within about 100 light years of Earth. So they're really just starting this. And they're looking through
so when you say that, sorry, so they're looking through, say, the current known current confirmed
yeah, that's
exoplanets.
what I was about to get to. Yeah.
Yeah. Okay.
And they've sifted out the ones that would be the most likely. They're not just looking at every single super Jupiter and all that, but it's the ones that are going to be about the size of Earth, around the right kind of star. They found a sample of 24. They're going through more of them, but they didn't find any super habitables. They did find one that had 4 of the 5 criteria, but none of them had all of them. But really, where the value of this study is that once we locate a certain number of these, that we can then start focusing like observatories like JWST and these ground-based ones we were just talking about with a really good instrumentation to say, okay, and also LUVOR, which will be upcoming, to say, okay, we found these things. Let's take, what can we find out about their atmospheres? What can we find out a little bit more about their characteristics, their masses, and that sort of thing. So that's the value of this. It's really a starting point to figure out what are these kinds of planets that we could have that would be fostering more complex life.
Yeah, I mean, when you think about, say, upcoming missions like HabEx, which is going to have this star shade that's going to be flying 75,000 kilometers away from the telescope, you've got to line up your telescope and your star shade perfectly to get the planets to be able to be observable nicely. And you're not going to get a lot of shots of this. You're going to get 10 throughout the lifetime of the mission. And so it makes a ton of sense to go after the lowest hanging possible fruit, which is going to be these planets that are orbiting these chill stars that clearly have a lot of mass, that are right smack dab in the place where they could have water. And you would just end up with your best shot at searching for that phosphine on
Well, and the other thing I was thinking too, I did some more reading on this, is that you're probably not going to have any kind of evidence right away of just microbial life. So it really is going to be the search for the higher forms, more multicellular and more complex life, which is where they were going with this.
Yeah. No, absolutely. I think it's fascinating. And it's funny because a lot of people are like, they all, one comment that I got from people was like, oh, so you mean we should change the climate of Earth to be better? And like, super habitable does not mean super habitable for us. It means super habitable for aliens, not Earth life. We could end up on that world and it would still be utterly inhospitable to us. It's just that for every square kilometer, we've got X amount of biodiversity of different species. They would have 2X or 10X.
10 or 10. Yeah. So it's really about trying to find, these higher life forms. I mean, ultimately everybody wants to talk to an alien, right? But we just got to find the evidence first of where all these things are that would be affecting their atmospheres and that would also be, fostered by these bigger, more atmospheric planets.
Do you know if any of these are easier to find than others, or easier to study? Like we've been finding a lot of planets around the M dwarfs, around the red dwarfs, because they have such low mass that you can find, they used to use Alan's analogy, right? They're small children holding a fairly big bucket as they're spinning themselves around. But they probably are very mediocre for life. So do we know like which of these would be easier to study?
Yeah, well, it's still going to be a technical challenge, right? To separate this thing out from the light of its star, even in the Goldilocks zone, unless it's on the really far edge of it. But I don't think we know that yet.
Yeah. And it's interesting too, that idea of like, you would want to have more gravity. I mean, once again, we have a very Earth-centric concept. David, what do you think about higher gravity and its impact on life?
I'm getting a thought about Goldilocks zones and high gravity, because one of the perspectives that we have, not for super habitability, but for habitability overall, is this original idea that we've had for decades that you have to be in the Goldilocks zone in terms of surface water does not necessarily apply if you've got tidal heating of an interior ocean, allowing an interior ocean, because you got tidal heating of water ice, as we do on Europa and Enceladus and other gas giant moons. But I'm thinking if you had, say, a very large terrestrial planet, for a terrestrial planet, if you had a multi-planet system, say two big planets orbiting one another, and you got tidal forces between these two super Earths, you can have heating inside, which means you can have an internal ocean, just like you have on these much smaller planets, these moons of Jupiter, Saturn, and the other gas giants. So, I'm just sort of speculating, but
but I sort of wonder, like, if you had some kind of creature that was attempting to walk around on the surface of a planet with 10% more gravity than Earth, or 20% or 50 or twice the gravity of Earth, it would have thicker legs, but it's still
the physiology would be different.
But in theory it should still be, flying would be a little more difficult, although perhaps the oxygen would be more thick. So it'd be pretty fascinating to kind of imagine the kinds of life forms. I know Carl Sagan did a whole bunch of this.
Fraser, one thing I forgot to mention too is that you have to have internal activity in these worlds. They can't be like Mars with not a lot. It's because you got to be able to generate a magnetic field.
And that's the benefit of that. You were mentioning that earlier, right? That's the benefit of that bigger world, is it's not going to cool down. It's probably going to still be toasty inside and have a lot of plate tectonics. Exactly. Yeah, fascinating. All right, we don't have a lot of time left. Nika, what have you got for us?
Hi. So there are some, Germany's planning its first spaceport.
What?
And maybe just in 1.5 years, there will be rockets launching into space from Germany. So there are even two sites seriously taken into the consideration. So the Federation of German Industry brings a launch site in the North Sea into play, and the German Aerospace Center is planning the Rostock-Lager Space Airport. So there are two things going on. So for now, Europe had to use the Europe Space Center Kourou in French Guiana for all launches. So the spaceport is around 7,000 kilometers away from Germany, and it is designed for big launchers like Ariane or Vega. So to find a launch platform for small launch vehicle is difficult in Europe. Therefore, these two sites would make many mini launchers very happy, especially three German startups called Iser Aerospace, High Impulse, and Rocket Factory Augsburg that are currently designing the mini launchers.
So let's talk about these different kinds of platforms.
Correct.
So I've pulled up the article, and kudos, I think you utterly scooped. You got a total scoop here, because I have not heard about this news at all. And in fact, the only article you were able to find was in German. So again,
there are many articles in German.
Yeah. Thanks for bringing the European perspective.
English.
This is amazing.
Yeah, correct. I know that because I have some friends in the German Aerospace Institute, and they're working on the study that I'm going to talk a little bit later. So they're like, oh, there's cool stuff going on. So basically, for example, for the North Sea platform, this whole concept was already presented to the government. And the idea was to use the existing platforms that are used for the wind turbines and just reuse it and convert into the launch platform. And the cost was estimated to be around 30 million euros for the conversion and operation, like as initial cost, which is not that big.
No, it's not that much.
Actually. Yeah. So this project is already.
So this would be, sorry to understand. So this would be out in the ocean,
in the
and it
North
would be
Sea.
an old wind platform in the North Sea, and it would be a place to launch rockets. And
correct.
I mean, one of the problems with Europe is that if you want to launch rockets in the direction of the Earth's rotation, you have to launch them over land. And as we've seen in China, that's not your best move. So would these be polar launched rockets? Would they be, what kind of trajectories would they be going for?
Yeah, Correct, absolutely correct. So unfortunately, you have too many people. Also in the sea, you have too many ships. So you have really restricted to the areas where you can launch anything.
Well, you want to launch east to take advantage of the Earth's rotation if you want to go into orbit, to follow the, if you want to be able to take advantage of the Earth's orbital rotation. So, but a polar orbit works great too.
And yeah, basically that's a polar sun-synchronous orbits.
Right.
And that's would be almost there's no chance to do something else.
Right.
Because this area where it is safe for the launch is there was a map I can show maybe on some other video, so that it's very narrow. It's like you can't, because like if you look on the Europe, you can see on all the sides there is like Britain, UK, and there's on the other side Norway and so on. So, and there's islands as well. So you have very like narrow area.
Right.
And you can only use just that.
Right.
And there's but polar orbits are very like popular, and sun-synchronous orbits are very much needed.
Yeah, I mean, the power of a polar orbit is that it lets you essentially be able to access the entire planet, while a equatorial orbit, you have to remain in whatever equatorial belt your spacecraft is launched. With the polar orbit, you can go around the whole planet, top to bottom, and image any part of the planet. So it's a very useful orbit. So you talked about this one kind of launcher, which would be a refurbished wind farm. What was the other idea you're talking about?
The other, it was also a study conducted by the German Aerospace Center, and they determined like one specific airport, which is a regional airport in Germany called Rostock Lager, and they determined this airport could be suitable as a space airport. So basically, with some small refurbishments, adding some infrastructure, you can basically create a spaceport in Germany, but there would be no vertical rocket launches.
Right. It would be horizontal rockets. Okay, so it would be like the Spaceport America in New Mexico. You would be launching air-launched rockets with airplanes, and then they would be releasing their rockets and then returning to the landing pad.
Yeah. So in this, like I saw this study, by the way, and in this study, they were taking few use cases, business cases, which might be interested. So this air launch, where you have like an airplane, which has a rocket added on the aircraft, or another aircraft, which you basically launch to a certain orbit, or you have something like space plane, like a Dream Chaser that would launch, for example, from the Cape Canaveral and land in Germany for like a specific certain mission.
Right.
So, and so the DLR is proposed, so this research center that was conducting this study for the government as well. So they are proposing a pilot mission for the air launch in Rostock for 2023.
Okay.
So it is, and in around 2023, there would be first launches from this North Sea platform as well. So now it's just a matter of the politicians and politics to make all this regulations and, of course, the money available for this
now. But I mean, there's a country just to the east of, in Eastern Europe, Russia, which has worked out lots of ways that you can launch rockets from Europe. And as well as places like Kazakhstan, but it's interesting to see. But as you said, that Europe right now, I mean, there is a launch facility in Sweden, but it's for smaller rockets, and then of course the Russians will launch you an old ICBM off of a submarine as well. So if you want to do that, but I think this is great. That sounds pretty fascinating.
You're done. Sorry.
Yeah, no. We're sort of reaching the end of our hour, so I don't want to take any more of people's time. But I look forward to this progress, either one or both. It sounds like a bargain. It'd be kind of cool to imagine, say, Falcon 9s flying from Europe on a.
Why not?
Why not? Yeah. All right. Well, you're on my screen now. So why don't you tell us what you're working on and where people can find out more, Nika?
So follow me on Twitter, Veronica Space. If I will be doing any new projects, which I am planning, I just don't want to tell in advance. I will definitely tell it on Twitter.
All right.
So.
Excellent. Alan, what are you working on and where can people find out more?
You can find me on Twitter as well, Astronomer, Urban Astronomer, and I am in the middle of the third season of the Urban Astronomer podcast, which you can subscribe to directly by searching for it or at urban-astronomer.com, or just listen to 365 Days of Astronomy, where episodes tend to come up about a month after they were published originally.
Fantastic. Carolyn.
You can find me at thespacewriter.com, and I'm also on Twitter at I think I just changed my name, at the Space Writer. Yeah.
And what are you working on?
I'm working on a full dome show about exoplanets right now.
Oh, fantastic.
So, yeah.
Will people be able to attend it?
That's another good question. We could probably go for an hour about that.
Yeah, I know.
Not right at the moment.
Yeah.
Not right at the moment.
All right.
Yeah.
Well, David, you stuck around, so you get to let us know what you're working on and where people can find out more.
Yeah, so and that's good because I forgot to say the company that is running this is called Mgenuity, based in Princeton, New Jersey. I'm not in Princeton. I'm in Portland, Oregon. We're all spread out, but we don't have a website for the project yet because we don't know how it'll go. It's just a phase 1. We hope we'll get to phase 2 though. If we do well in the phase 1,
you should totally do a website. People are going to love this.
Yeah. I think I don't know where you got that picture, but it was pretty cool what you put for the promotional for this episode.
That would have been Nancy. I'm not sure where she found it. Yeah.
Maybe she got it from the Mgenuity website.
Yeah.
I'm not sure, but you can find me on Twitter at Cosmic Evolution. You can find me on Instagram under my name, David Warmflash. Also, the book has an Instagram, Moon Illustrated History.
Fantastic.
The other places.
Great. All right. Well, so we are going to attempt again to do our virtual star party on Saturday night. Let's hope the sky clears, the smoke settles down, and we're able to open up the telescopes and be able to show you the night sky. So we'll find out what happens. The fact that Carolyn is saying there's fires in Colorado, and I know there's still some fires, still some smoke in the sky here. I hope in Canada from the U.S. fires. I hope. I'm a little nervous, but Mars at opposition. We've got to be able to show you this. So we'll know what's going to happen there. All right, I'm going to put everybody up on the screen again. There we all are. There's all of us. So thank you, everybody, for watching us on the Weekly Space Hangout. Thank you to all of the moderators, and thank you to my co-hosts. As always, it's a pleasure hanging out with you guys and our special guest. And we will see all of you next week. Thanks, everybody.
Bye-bye.
Bye.
Bye-bye.
And how do I stop this? All right.